This is example 11 in our vectors topic, and we spent a little bit of time in the previous examples looking at how to find the equation of a straight line in 3 dimensions. If you haven't seen that, examples 6 to 10, which is one big long video taking you through the different forms, then have a look at that first of all. So I'm assuming that you've looked at that video, and we're now going to practice it using some of the information here. So we've got 3 things we're going to find out. It says find the equation of the line joining 2 points. So we've got point A and we've got point B, and we're going to find out first of all the equation of the line in symmetric form or symmetrical form, and we're going to then express it in parametric form just by doing a bit of algebraic rearranging, and then we're going to do something a little bit different. We're actually going to find some other points that lie on the line, just arbitrary points based on values that we choose. Okay, so we'll come to that shortly, but let's have a look at part A and B. So we need to find the equation of a line. The ingredients for finding the equation of a line are that we need a direction vector, and we need a point that lies on the line. So we need a direction vector and a point. We have got 2 points here, so we're stuck for choice here. Spoiled for choice rather. We've got 2 points to choose from, but the direction vector we don't know yet. What we do need to work out then is the vector AB. That's going to be our direction vector. So we can say that AB is the point B minus A. So we've got position vector B and position vector A. And we're left with 4, 1, negative 2. So effectively we've got this line that passes through A and B, and the vector AB we're going to then say is actually our direction vector. So we can say that D is going to be that as well as AB. Okay. We are also going to take one of our points. It makes absolutely no difference at which point that we're going to use. So I'm going to use 0, 2, 3 as our point that we're going to use. So symmetrical form is the easiest one to make up. So the equation of the line in symmetric form looks like this. We've got x minus, and a line equals y minus something over something, and z minus something over something. And I like to also sometimes make sure that you know that they're all equal to some parameter. And so we've got 2 numbers to fill out in each fraction. The bottom number is going to be our direction vector. So our 4, 1, negative 2 goes here, here, and here in order of x, y, and z. And the top numbers are going to be my point. Okay, so I've got 0, 2, 3, 0, 2, 3. So obviously I've got 0, 2, and 3. None of them are negative, so they all stay overall as a negative sign there. Remember, if it was a negative coordinate, one of them would become plus. So we can rewrite that as x over 4 is y minus 2 over 1 equals z minus 3 over negative 2. And again, if you want, you can keep that equals t. That's the equation of my line in symmetric or Cartesian form. We're asked in part B to give the equation of the line in parametric form. So let's just write that in. So what do we need to do to turn these into parametric equations? We need to split up our Cartesian equation into 3 different small equations. We have to remember that x over 4 is equal to t. Therefore, t is then, well, we could say, sorry, that x is equal to 4 times t. And that's our parametric equation in x. We can say of y minus 2 over 1 equals t. Y minus 2 over 1 equals t. So that tells me that 1t is equal to y minus 2 equals t, y equals t plus 2. So we're just rearranging it instead of t being the subject of our equation. It's going to be the x, y, or z. And in the last one, we've got z minus 3 over negative 2 is equal to t. So we can write that down. Z minus 3 over negative 2 equals t. Watch this one. Because we get z minus 3 equals negative 2t, z equals negative 2t plus 3. So we can actually say that the equation of the line, just to tidy that up, x equals 4t, y equals t plus 2, z equals negative 2t plus 3. Okay, and that's the equation in parametric form. So we've managed to come up with the equation in two different forms. The third part in C, nominating parametric values, find two other points that lie on the line. Effectively what that means is, in order to find C, the nice thing about parameters is here that we can apply t to be anything, and that will generate points on the line. So for instance, when t equals 1, for instance, then what we could say is that x equals 4 times 1, which is 4, y equals 1 plus 2, which is 3, and z is equal to negative 2 times 1 plus 3, which is 1. Do we have 4, 3, 1 as one of our nominated points at the top? Yeah, we do. Okay, so that's not going to be one that we can actually use because we've kind of already been given that. So, but that's the idea. So let's see if we can generate a few more then. What about when t equals 2? X is going to be 8. I'm just going to do this kind of mentally. It's not a difficult thing, but so that you know where all the numbers are coming from. When t is 2, negative 2 times 2 is negative 4. We'll get negative 1. So in other words, 0.84, negative 1 lies on the line. And you could pick any value of t. You could pick, we can't pick 0 because that's the other point that we had. Let's just pick an arbitrary value. When t is 5, then x is going to be 20, y is going to be 7, and z is going to be negative 10 plus 3, which is negative 7, i.e. 27, negative 7 lies on the line. So once you know the equation of a line in parametric form, which is at the top of the screen there, and you want to generate points along the line, all you need to do is to pick some arbitrary values for t, substitute in, and you'll get the matching x, y, and z coordinates, which is why it's a really useful form to use for that kind of purpose. So that's the idea of example 11. Hopefully you've got some stuff to work on there.